One of the factors that affect rate is concentration. And we saw that reactions go slower and slower as the reaction progresses. That's because we're consuming reactant. Now, concentration gives us a way to study kinetics. In fact, we say the effect of concentration on reaction rates is often studied. And one way we can study that is we can run multiple experiments where we change the initial concentration and measure an initial rate and see what effect concentration is playing on rate. When we understand just how concentration is affecting rate, we've deduced the rate law. At the beginning we looked at some rate expressions. We don't really want to confuse that with the rate law. The overall concentration dependence of reaction rate is given in a rate law. And it has this typical form. Rate is equal to some constant times reactant 1 raised to some power times reactant 2 raised to some other power. So that constant K, that's lowercase, is called the rate constant. The exponents M and N are called reaction orders. And the overall reaction order is the sum of the reaction orders. So how do we determine what a reaction order is? Let's just think about this a little bit. We'll just imagine one reactant, and that's a good idea. We just have one reactant, the overall reaction order and the order with regard to that one reactant are the same. If a reaction is zeroth order in a reactant, changing the initial concentration will have no effect on that rate. Maybe we could do that on our calculator. What is anything raised to the zeroth power? 1. If a reaction is first order in a reactant, doubling the initial concentration will cause the rate to double. If a reaction is second order in a reactant, doubling the initial concentration will cause the rate to quadruple. So if a reaction is nth order, any type of order, doubling the initial concentration will cause the rate to do this. Fortunately or unfortunately, we can double a reactant, and most of us know our powers by 2, so that's convenient, but we could triple a concentration, we could half a concentration, and we try and design experiments so it's somewhat straightforward. So here's a reaction where ammonium cation reacts with nitrite, and we do 6 experiments, and we see what effect it has on rate. So if I look at experiments 1 and 2, I'm holding nitrite constant, so any change in rate is not going to be due to this reactant. What do I do here? I go from 0.01 to 0.02. It looks like I've doubled the concentration of ammonium, and what did that do to the rate? Looks like I've doubled the rate, so that looks like first order with ammonium. Alright, now I need to find an experiment where I hold ammonium constant. Looks like all 3 of these. I'm holding ammonium constant. What am I doing here with nitrite? Here I double nitrite. Experiments 4 and 5, I double nitrite, I hold ammonium constant. What happens to the rate? It doubles as well. That means this reaction is first order with ammonium and first order with nitrite. So there's the unwritten but understood exponent of 1 and 1 there. So the units of this rate constant have to be such that we get units of rate. Here are some units of rate and the overall reaction order. So we're going to just imagine there's one reactant. Units of rate, we're going to have the rate constant times units of concentration raised to some power, which depend on the overall reaction order. So here is a typical determine the rate law problem. Reactant A and reactant B go to products. And so we do some experiments where we measure initial rate and look and see how our starting concentrations affect rate. So our rate law, when we start out, we know it's rate is equal to some constant times the concentration of A raised to some power times the concentration of B raised to some power. I'm going to call those M and N right now. We don't know what they are, but we're going to figure them out, and that's called determining the rate law. And we can probably do this by just looking at what's going on, but maybe it will help us to visualize possibly another way to do things. I like to come up with this thing called the rate factor is equal to a concentration factor raised to some power. So let's just do that. We're going to look at experiments. So my rate factor is 2.83 moles per second divided by 2.83 moles per second. What's my concentration factor? Well, this is to figure out what's going on with reactant B. Sorry, I had those switched. We want to compare 2 to 1. We could figure it out doing it the other way, but myself and other people don't like to deal with fractions. So my rate factor, it comes out to be 1. I don't need my calculator for that. I probably don't need my calculator for this one here. That is 2 raised to the x. So what must x equal? Don't everybody shout it out at once. Yeah, 0th order. 2 raised to the 0 equals 1. Well, we didn't need to do that. I doubled the concentration of B, and it had no effect on rate. Now I get to come over here and put a 0. So now it doesn't matter what we're doing with B. Say I just walked in and I didn't know this yet. I could have said, let's figure out what's going on with A. If I want to figure out what's going on with reactant A, I'm probably going to compare these two experiments because I'm holding B constant. If I didn't know this other information, that's what I'd do. So I'm still going to come up with a rate factor. I'm going to go 25.47. That's experiment 3. I'm going to compare that to experiment number 1 because I'm holding B constant. All right, and I got 2.83. There is my rate factor. What's going on with my concentration factor? Experiment 3, I start out with 0.819 molar. In experiment number 1, I got 0.273 molar. And this is raised to some power. So 25.47 divided by 2.83. My rate is increased by a factor of 9. That's my rate factor. 0.819 molar divided by 0.273 molar. I've increased my concentration by 3. 3 to the what equals 9? Squared. Absolutely. Y equals 2. So now we've determined the rate law. So we know this is a 2. So then at that point in time, we're going to write something like this. Rate equals rate constant, concentration of A squared. Now we know how the rate is affected by concentration. We know that it's 0th order with B, because changing B has no effect on rate. We know it's 2nd order with A, because when we triple A, we've increased the rate by a factor of 9. Well, that's a good place to stop.